Okay, now we're going to look at calculus with parametric curves. So now we're going to be able to determine, we already know what a Cartesian curve looks like. And we already know how to find the derivative of a Cartesian curve, whether we just use a regular derivative, whether we use a quotient rule, product rule, the chain rule, any of those things apply. The question is, how do you find the derivative of a curve that is parameterized with a t? Because we're still looking for the slope of the tangent line to a particular curve. Okay, so now we want to look at these tangent lines to parametric curves. Then beyond this, we're going to find the area under a curve, we're going to find the arc length, and we're also going to find the generated volume and surface area of a parametric curve when you revolve it around a particular axis. All of these using the parametric form. Okay, so let's start off. So first off, we already said that we know what a parametric curve looks like. So I'm going to have a definition. This is my first thing I'm doing in this section. All right. So definition. We talked about closed curves. So now we want to talk about what it means to be a smooth curve. So a parametric curve all right, C, where X is equal to F of T and Y is equal to G of T. Is smooth all right, if F prime of T and G prime of T are continuous and never simultaneously zero. So they can't be, one can be zero, but the other one can't be. Okay, so that makes it smooth. So we want to choose a point T naught and a neighborhood, we're going to call it I, about T naught. So I'm only looking around one point. All right, so let's let F prime of T naught be positive on this interval I. All right. So therefore, F of T is an increasing function on the interval I, and therefore it has an inverse. Okay, so now we're going to say we have X is equal to F of T, and it has an inverse function T is phi of X. So we get Y is equal to G of T, but G of T is just G of phi of X. So therefore I can write Y as a function of X. It's G of phi of X. So y is a function of x. And then similarly, it's a hard word for me to say always. For g of t, I can do the same thing. And so therefore I can write x is some function of y. All right. So now given y is equal to f of x, the curve, we can compute dy dx. So this is how we're going to do it. We're going to use the chain rule. So we're going to use the chain rule. And this is so easy. We have dy dx is the derivative of y with respect to t times the derivative of t with respect to x. Now remember, t was equal to phi of x, so we know that exists. So that's my chain rule. But this is the same as saying dy dt times 1 over dx dt. And there you have it. Dy dx is dy dt divided by dx dt. And that's how you find the derivative in terms of dy dx when you know that you have a parameterized curve. Now here, we're going to assume dx dt is equal to f prime of t is not equal to 0. So if it equals 0, you have a vertical tangent. Okay, so if dy dt is equal to 0, then you're going to have a horizontal tangent. And if dx dt is equal to 0, you're going to have a vertical tangent. Okay, so this is fairly easy. So here's an example. So x is equal to a the cosine cubed of t, and y is equal to a sine cubed of t, and then t is between 0 and pi. Okay, so dx dt, well, that's just 3a cosine squared of t times minus the sine of t. So that gives me minus 3 or negative 3a cosine squared t sine of t, and dy dt is 3a sine squared t times cosine t. So that's positive 3a sine cosine of t sine of t, sine squared of t. So dy dx is dy dt divided by dx dt. So I get negative 3a cosine t sine squared t divided by positive 3a cosine squared t times the sine of t. And that gives me negative tangent t. All right, so the numerator and denominator all right, both equal 0 at any multiple of n pi over 2. All right, so you get cusps. You get horizontal tangents when the numerator is 0 and the denominator is not equal to 0, and that doesn't happen. And you get vertical tangents when the numerator is equal to not equal to 0, denominator is equal to 0. That doesn't happen either. Okay. So let's look at the cycloid. Once we derive it, we can use it. So we said x is equal to a times t minus the sine of t, and y is equal to a times 1 minus cosine t. So therefore, dy dt is a times the sine of t. And dx dt is equal to one minus cosine t. I'm missing an a. A times 1 minus cosine t. All right. So I get that the slope dy dx at any point is equal to the sine of t divided by one minus cosine t. Okay, so when is the slope equal to 0? So dy dx equals 0 whenever t is a multiple of pi. Aha, that's not right. Why is that not right? I caught myself. Because what I did was I looked at the numerator only. And I said, when the numerator is 0, t is equal to n pi. Because the sine of n pi is 0. But the problem is the denominator is also equal to 0 whenever n is even. Does everybody see that? I made that mistake. Okay. So that is not true. So let me erase this because dy, that's not true. So let's say the sine of t is equal to 0 whenever t is n pi. All right, so that's any multiple, n equals 0, 1, 2. Okay. And the cosine of t, 1 minus the cosine of t is equal to 0. Whenever I get 0, 2 pi, 4 pi, or 2n pi. So I need to throw away all of the even ones. So therefore I get dy dx is equal to 0 when t is only an odd multiple of pi. Okay. And then, so these are horizontal tangents. And then I get when the numerator. So how do I want to say this? Okay, I get no vertical tangents. So we get dy dx we get vertical tangents when the numerator is not equal to 0, but the denominator equals 0. And that never happens. But they're both equal to 0, we get cusps. So that's when the numerator is equal to 0 and the denominator is equal to 0. And that's t is equal to all the even multiples of pi. Okay. Let me think about that for a moment. All righty, I think we're good. All right, so here are going to be my horizontal tangents. As you can see, if I go back to my picture from before, my horizontal tangents are right there. All right. And here are my cusps at even multiples of pi. Okay, so that looks good to me. All right, so I get cusps. All right, so that is how I find the derivative. Suppose I want to look at concavity. Okay. So if I want to look at concavity, that means I'm looking at the second derivative, right? So how do I do that? How do I find the second derivative? D squared y equal to dy squared. Anybody have an idea?
Dr. Law, can you hear me?
Okay. Oh, no, now I can. Now I can.
Okay, I said you take the derivative of the derivative.
Okay, so we would take the derivative of the derivative. Okay, so the derivative of the derivative would be to take the derivative with respect to x of the derivative of y with respect to x, right? So that is the derivative of the, so how do you take the derivative of anything? Well, to take the derivative of anything, that would be the derivative with respect to t of dy dx divided by dx dt. So then that says take the derivative of dy dx. Well, dy dx is dy dt over dy dx. So you dx dt. So you would get the derivative of dy dt nope, I'm writing it wrong. It's the derivative. This is the derivative with respect to x of dy dx, right? So that becomes the derivative of y prime with respect to t divided by dy dt. Oh, that's right. So this is just wrong. This is the derivative with respect to t over, that's right. Okay. So you just need to take the derivative with respect to the y problem and then divide by dx dt. Okay. So where are we? So dy dt was dy dt was a sine t. And then dy dx dt was a times 1 minus the cosine of t. So therefore, we need to take the derivative of dy dt. So what do you get? The derivative of, this is wrong. This is dy dx. Derivative with respect to t of dy dx. And then divide by dx dt. That's right. Okay, so what did we get for dy dt? So dy dx we ended up with sine of t over 1 minus cosine t. All right, so therefore we take the derivative with respect to t, so d squared y dx squared. We're going to take the derivative of this, which is the bottom, 1 minus cosine t, times the derivative of the top is cosine t, minus the top, which is sine t, times the derivative of the bottom, which is sine t, and then divide by the denominator squared, which will be 1 minus cosine t squared, but then we have to divide by dx dt. So that dx dt is a times 1 minus the cosine of t. And that simplifies to negative 1 divided by a times 1 minus the cosine of t squared. And that's cool because it's always less than 0, so it's always concave down, and that is exactly what we get. We get that, which is always concave down. Okay, nice, cool. Okay. So let's recall some formulas because we're going to change these formulas into formulas that have parameterizations. So we're going to go back, way back. So let's do a recall. Thank you, Layla, for your help with that equation. All right, so let's write them all out. 1, area under a curve, that's easy. So the area under a curve, A, the integral from A to B of y dx. Remember, y is equal to f of x, so that's the area under a curve. 2, the volume, let's do the arc length of a curve first. What do I do? Volume of revolution, it doesn't matter. Volume of I'll do them in the order that I have them. Volume of revolution around the x-axis. Okay, so if you remember, we're going to do this very simply and use a disk method. Okay, so we're only talking about that right now. So we get v sub x, that volume is then the integral from A to B is pi r squared, where r, if you remember, was just the height of the function dx. And then the volume of revolution around the y-axis. So now we're assuming x is equal to g of y. So that volume is the integral from c to d of pi times x squared dy. So that's number 3. Number 4 is arc length. All right. So we have some curve. And if you remember, arc length looked like the integral. So we said L, the integral from A to B of the square root of 1 plus the derivative, which was dy dx, or y prime squared dx. Area of surface of revolution well, that required also the arc length. All right, but for this one, this is about the x-axis. So that area, the integral from A to B of 2 pi, the radius was just y, and then we use the square root of 1 plus y prime squared dx, the area of a surface of revolution. And then I want to do about the y-axis. That area the integral from C to D of 2 pi x square root of 1 plus x prime squared dy. Okay, so let's figure these out in terms of, oh, I see I have something in the chat. Oh, that's old. Okay. All righty. So let's consider a smooth parametric curve. Okay. What's new? What's new? Anaya, what's new?
Yes, I'm sorry. I asked the question and then you said that it was old. I just asked it. I'm sorry.
No, wait a minute. Go ahead. Tell me, what do you mean what's new?
Oh, because you said it was something in the chat, but I don't think you read it. I asked when you were gonna post the YouTube links. That's why.
Oh, that's what's new. Okay, as soon as it comes. The other one I'll post right away because I have it. But this one,
Okay,
I'm going to have to wait for these. Yeah, they usually take about an hour or two, and then they have to upload to YouTube.
Okay, thank you.
No problem. All right. All right, so here's my smooth curve. Nice smooth curve, right? So it's going to go something like this. It's going to start here, and it's going to go up like that. Okay, so it's going to start at some t. All right, so t is equal, so just let's look at this curve. So t is going to go from t is going to go from alpha to beta. Okay, this is my point A, and right here is my point B. So I'm going to have x is equal to some function of t, and y is also now going to be g of t. All right. And so t is going to go between alpha and beta. So on the interval AB, we're going to assume f is increasing or decreasing. These are very, very nice functions. Okay. So f, and if it's not increasing or decreasing, we can break it up into several parts. Okay. So now notice that when t starts at alpha, I'm at the location A. So therefore A is f of alpha. And when t ends at beta, I'm at the point B. So B is equal to f of beta. All right. So for all these things that we're talking about, so let's consider every equation that I just mentioned. So consider every equation I mentioned. So I talked about the area, and then I talked about the volume revolution in X, the volume of revolution in Y. I talked about the length of the curve. I talked about the surface area of revolution in X and the surface area of revolution in Y. In all of these, we're going to make these substitutions. So the substitutions I'm going to make is X is f of t, and dx dt, I'm sorry, dx is going to be f prime of t dt. Y is going to be g of t, and dy is going to be g prime of t dt. Then I'm going to take the integral from a to b, and I'm going to move that to the integral from alpha to beta. So here's an example. So in my area function, I have integral from a to b of y dx. And that is very nicely going to move to the integral. Well, when I'm at A, if you remember, t was alpha. And when I'm at B, remember, t is beta. And then y is g of t, and then dx is f prime of t dt. And I'm going to do that if f of a is less than f of b. Or I'm going to write it as the integral from beta to alpha of g of t, f prime of t dt, if f of beta is bigger than f of alpha. Okay. I thought I had an example, but I don't. Okay. So we're going to change. So let's go on to the arc length for a moment. So dy dx is, remember, dy dt over top of dx dt. But that's just g prime divided by f prime. Okay. So my arc length L, the integral from a to b of the square root of 1 plus dy dx squared dx. So in the place of that, I'm going to change this to alpha and beta. I'm going to get the square root of 1 plus. On the top, I'm going to put g prime of t. And on the bottom, I'm going to put f prime of t. I'm going to square that. And then on the outside for dx, dx is f prime of t dt. So now when I put f prime of t inside the square root, g prime of t squared over f prime of t squared. And that whole thing multiplies by f prime of t squared. So when it goes inside the square root, it goes inside squared. So now I get that the arc length is the integral from alpha to beta multiplied by f prime of t. So I'm going to get f prime of t squared plus g prime of t squared, and then that's going to leave me dt. So there's my arc length. And here's my area. Okay. All right. So before I go any further, I think we need to understand what's going on here. So I'm not going to get a chance to finish this. We'll pick this up tomorrow. So I need to find the length of the asteroid x is equal to cosine cubed t. This should look familiar to you. Y is equal to sine cubed t. 0 less than equal to t less than equal to 2 pi. So here a is 1. I did one earlier. So it looks like this. I am not the greatest drawer. Okay, it's not horrible. It's not horrible. Okay, so now actually in order to find the length of this, I really only need to find the length of one piece. Okay, so if I can find the length of this piece right here, then I can multiply it by 4. So that is where we are going to start in recitation tomorrow, is working problems.